Hi, my name is Joshua Proctor, and I'm going to be speaking about a recently published article in the SIAM journal on applied dynamical systems called Dynamic Mode Decomposition with Control, DMDc for short. Now, this work was done with my colleagues at the University of Washington, Steve Brunton in the Mechanical Engineering Department, and Nathan Kutz in the Applied Mathematics Department. I'm from the Institute for Disease Modeling in Bellevue, Washington. Now, one of the major motivations for the development of DMDc is the fact that there are a staggering number of preventable deaths each year. In fact, over 6 million children die globally per year. Now, the hope is to develop quantitative methods to help analyze infectious disease data and inform policy decisions which can allocate resources for preventing these deaths. Now, we know from a great achievement in the 20th century that we can eradicate human infectious diseases, and we've eradicated smallpox, and actually we're quite close to eradicating polio with fewer than 100 cases per year of paralyzed children in only a few countries. Now, the type of infectious disease data that we're going to be looking at for the methods of DMD and DMDc has a very strong spatial-temporal characteristic, and so here are two different data sets from the Google Flu Trends tool on the internet, as well as measles cases in the pre-vaccination era of the United Kingdom. On the x-axis here, we have time by year, 2004 to about 2015 for the flu, and 1944 to 1966 for the measles. On the y-axis, we have place in the United States for the flu, and the United Kingdom for measles. Now, taking each time series, so each row being the number of cases at a particular place, we can actually normalize this data, so setting the mean to 0 and the variance to 1, allowing us to visualize the particular seasonality across rows and places that might have substantially larger populations. And you can see very strong spatial temporal characteristics. With flu, as we expect, each year, most places get flu right around about the same time with a little bit of variation. In the measles data set, you see a seasonal effect, but there's more nuance and more interesting temporal characteristics. But the takeaway is the fact that this type of data has a very strong spatial temporal characteristic. Now, normally, or at least classically, you would model these infectious diseases with compartmental models, and this is where individuals are grouped according to a particular state to construct a pseudo-mass transport model. Now, what do I mean by that? Well, individuals would be grouped into, for example, susceptible bin. So if you're susceptible to becoming sick, you would be in an S bin. If you're actually infectious, you would be grouped into an I bin. And if you've recovered from the disease, you would be in an R bin. Now, we can describe how the processes work of either birth, death, vaccination, or becoming infected as a susceptible through a set of ordinary differential equations. These include a quadratic nonlinearity and have been very successful in describing epidemic behavior as well as endemic disease transmission. Interestingly, though, the more realistic you try to make these sets of equations and adding characteristics like, for example, age in this index I, you get this combinatorial explosion of states and parameters, increasing the complexity of the model and also increasing the requirement of more data to fit those states and parameters. Now, not only that, but if you have a high-dimensional model, it becomes difficult to design observation strategies or surveillance strategies, or even vaccination strategies or control strategies. This becomes difficult when you add on more layers of complexity. For example, how people move around in actual topology in a country. This is every LGA in Nigeria, 777. So now you're not only fitting how the disease is evolving within a population of people, but how people are moving around a particular country. So in this talk, I'm going to propose a complementary method that moves away from using model-based kind of descriptions of the disease data and using a more data-driven model reduction technique on historical data. And this looks for coherent structures in time and space of the data, which could help constrain the modeling, so how many places you actually have to model or what types of states, and intuitively help understand the spread of disease. Now, dynamic mode decomposition is a powerful method that has been evolved out of the fluid dynamics community by first Schmidt and then subsequently by Clancy Rowley in Princeton University. And the method goes something like this. At a high level, you collect your data. data alone, no models, and this could be from numerical experiments, laboratory experiments, or just historical data, and you form these into state snapshots in time. Now these are state measurements, so number of cases at a particular spatial location, or maybe the velocity of your fluid at a particular location in your channel, and you put those into a single state snapshot matrix X1. And then you form a bunch of measurements in time all the way to XM. Now you vectorize all of your measurements in a single state snapshot, even though the location might have spatial structure, into a single column. Now you then have your data matrix X and a time-shifted data matrix X prime. And we really want to do is find a method to understand how these data snapshots are related in time. So we want to find an operator A that takes this from X to X prime. And if you think about that intuitively, what that means is we have an operator that takes us from this column, X1, to X2, and then from X2 to X3. And the characteristics of A tell us something about how this data is evolving, which has been collected from a dynamic process. So now DMD, the actual algorithm for computing dynamic mode decomposition, is quite simple and is only about 5 lines of code with a singular value decomposition on the data snapshot matrix X with a truncation value, an eigenvalue solve on an approximation of our operator A. Now, the output of DMD becomes eigenvalues of our approximation operator A and eigenvectors, which are also called dynamic modes. Now, for each eigenvalue that comes out of DMD, we get a temporal characteristic. So let's, for example, we have eigenvalues that are within the unit circle here, indicated by 3 and 4. That indicates that we have a decay term with a particular spatial-temporal structure. We have eigenvalues on the unit circle, which are indicating an oscillatory behavior. For example, that seasonal effect you see with Google flu. Now, with each of these eigenvalues, now is associated a particular eigenvector or dynamic mode. So you know which places are actually contributing to that particular temporal frequency or growth or decay. Now, for example, you could have eigenvalues outside the unit circle, which could indicate an epidemic is happening, and that dynamic mode would tell you where that epidemic is happening or how much each place is contributing to that epidemic. Now, here's an example from the fluid dynamics community and Steve Brunton in particular. This is flow past a cylinder, a traditional example from fluid dynamics, and you see these shedding vortices in this beautiful movie. Now, to apply DMD, you would collect your data from this particular experiment, this numerical experiment, and here we have X1, X2, X3, so our state snapshot matrix, where now we have measurements of the whole channel at time 1, measurements of the whole channel at time 2, and so on to XM. We'd form our data matrices or organize them into our vectors, and we really want to find the relationship from X to X prime. Now, what you get out of DMD are dynamic modes, shown here on the left, which represent these coherent structures in space, and then the type of time characteristics associated with those spatial modes. Now, here you have kind of a mean flow and then different oscillatory frequencies, each of these modes broken up into characteristics. Now, often we think of DMD as being able to provide intuition about the type of data that we've collected, but we can also use it for future state prediction. If we know how to build up our data matrices based on these modes, we can then use those modes to predict the future. Now, infectious disease data, in particular, often comes with associated intervention data. So how do we include inputs or exogenous inputs or control within the DMD architecture? Now, this leads to the development of DMDc. Now, to motivate this, here is wild poliovirus 1, type 1, by month for about 6 years. Each of the larger tick marks is January on the x-axis. On the y-axis is number of paralyzed children for those months. And you see this interesting temporal characteristic of polio cases. But more interestingly is we don't only have state snapshot information here, we actually have input information in time. So each of these colors of the rows, when it's either purple or blue, indicate a vaccination campaign occurred during that month. Now, the different colors indicate that the vaccination campaigns had different vaccines associated with them. So we're pushing on the system on a system that already has its own dynamic characteristics. As a second example, we can look at malaria. So this is malaria incidence in time. This is 2010 to 2015 in Africa, and these are estimates from the Malaria Atlas Project. On the second row, we have the insecticide-treated bed nets, which are interventions for malaria. And you see the distribution on the second row, indicating that not only is malaria evolving in time based on its own dynamic processes, but we're pushing on it with exogenous inputs. And these two are related, and we can't apply the standard DMD architecture without modifying it. So this leads to a slightly different interpretation of the data, and that is now including a set of snapshot measurements of your inputs or your control. And again, we vectorize those inputs into a matrix upsilon, and we want to find a method for analyzing this complex system with exogenous inputs that now finds two operators, or best fit operators, A and B, which now tell us how X evolves to X prime in the natural dynamics, as well as upsilon affects this system through this operator B. Now, this is an analysis tool for systems with exogenous inputs, and the hope is that it disambiguates the inherent dynamics from the effect of the input. And, it describes a sense of input-output space. Now, the output does not include the inputs, but the input space includes the current state measurement, as well as what type of exogenous inputs you might have. Now, beyond DMD, it actually now allows for a best fit operator of this B matrix, which tells you or describes the impact of input on your system. Now, algorithmically, not a lot has changed. So to compute this DMDc, we again form our snapshot matrices X, X prime, and upsilon. And instead of considering X and upsilon as different matrices, we're actually going to stack them into this larger data matrix omega. Now we're again going to use the singular value decomposition omega to find a factorization of omega. But now, and this is different from DMD, we're actually going to take a second singular value decomposition on X prime because the input space and the output space of X prime and omega are no longer the same, whereas in DMD they are. So we can find a representation of this operator A tilde being actually a low-dimensional representation. Then again, use eigenvalue solve to find the growth decay oscillations from the eigenvalues here in lambda and the associated dynamic modes. And this has now disambiguated the effect of states and inputs by only adding in another singular value decomposition and a little bit more complicated linear algebra. Now, as an example, we can look at dynamics evolving on a torus, and in particular, we can look at periodic boundary conditions of a 2D topology, pick out a small number of modes in Fourier space. So this is 5 different modes with a particular oscillatory frequency in 2-dimensional Fourier. This is a zoomed-in characteristic of this particular figure. And you can see as you project back into normal space, you get these interesting patterns. Now, we can apply inputs or control to this particular torus, changing the dynamics. But as long as we have measurements of the actuation on that particular torus, we get different effects of the control without control. Now, if we apply just DMD to that data that has inputs or exogenous inputs, we do not recover the exact eigenvalues of the system, which we know, nor do you recover the exact dynamic modes, which are represented here on the torus. But if you apply DMDc, you recover the eigenvalues exactly, which are pretty much right on the unit circle, and you recover the dynamic modes. So, and this is DMDc right here. So thank you for listening to me. Again, that was work that was recently published in the Dynamic Mode Decomposition with Control, DMDc, in the SIAM journal on applied dynamical systems. Thank you.